Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Brief introduction. I think I first met you when you were interning here with George Robertson. So that was what, 1994?
98.
98, okay. So yeah, it's been a while. I wasn't in visualization at the time, but now I come. And here, I think you're one of the premier professors teaching information visualization today. Just has a new book out, which I've had a chance to read, which is fabulous. And she is here today and at Tableau tomorrow. So please, if you have any interest in speaking with her, let me know. And we'll try to get her schedule's been filling up pretty quickly. So please welcome Tamar and looking forward to it.
Thank you. All right. So yes, thanks for the kind introduction. It has been a while since I have been back at Microsoft Research. So I've been working on this book project for quite some time. Turns out books take a while. Who knew? And so what I'm going to do today is not try to cover the entire book, which is not possible in an hour, no matter how fast I were to talk. I'm just going to hit a few key ideas and try to give a big picture, and particularly talk about the ways I try to frame the field that might be a little nuanced or different than what you might have seen before. So trying to focus more on the more interesting bits. So to start out with, let me talk about my own definition of visualization and some of its implications. And to save myself a few syllables, over the hour I will call visualization viz, because that's a word I will use quite a bit. So computer-based viz systems provide visual representations of data sets designed to help people carry out tasks more effectively. Now, why did I pick this particular definition? What are the implications of it? So for one thing, there's this idea that we've got data sets and people together in the same sentence. And in particular, that viz is suitable when there's some need to augment the humans instead of replacing them with something purely computational. So in what contexts does this happen? So I argue there's a lot of situations we don't need viz. We don't need viz if we've got something completely automatic that you trust. So the problem is there's a lot of situations where you've got an analysis problem that's not well specified. There might be one of dozens or hundreds or thousands or tens of thousands of questions that you might want to be asking, and you don't know a priori which they are. And so that's a situation where viz is typically a lot more suitable. Now, there's actually a spectrum of possibilities, and it could be that many of you might think really only on one side of that spectrum. So what I'll call the classic use case for viz is you intend it to be used in the long term indefinitely by some group of end users. And so that classic case is something like exploratory analysis, often with something like scientific data. But that's only one use case. So that kind of discovery use case is very common. There's also there's not just discovery of the unknown, but also presentation of the known. And that might be anything from things like graphics in the New York Times to any other situation in which you're not trying to discover something new with the viz, you're trying to present something you know to some audience of other people. But there's also these three other use cases that I want to make sure people are thinking about. And these are all, in some sense, visualization trying to work itself out of a job. So one would be you're using viz with the intent of later developing an automatic solution, but you need to understand it more. So you want to have some exploratory analysis towards the goal of model building. Another might be that you've already started building something automatic, and you could use the viz to try to refine it or debug it or figure out the right set of parameters. So often in that case, the viz is something for the developers of the algorithm, not for the target end users. Or it might be that you've even finished building the automatic system, but you've got to get the people that are going to use it to actually trust that it's right. So before you actually let it run unmonitored, you might have some situation where, again, the visualization is really, it's interstitial. It's trying to bridge the gap between the old practice and something that's new and fully automatic. Now, here's another interesting word in that sentence, visual representation. So why? What is the goal of having this visual representation, which is something external to your own head? And so the idea with this always is any time that we can replace something cognitive with something perceptual, then we have a win, where we've suddenly freed up internal resources for people to do something higher level. And so here's a very classic example. We have a table full of numbers. In this case, these numbers are gene expression levels that are measured after applying some experimental drugs. Now, if I ask you things like, find the minimum value, find the maximum value, even those really simple sounding tasks, what do you have to do? You have to read a number, you have to remember it in your head, you have to read the next number and compare it. And this is trivial if you've got two numbers, but once you start getting a few dozen, or I ask you more complex questions like, well, what's the distribution, not just min and max? This actually starts using significant amounts of resources internally. If in contrast, I take these numbers, and in this case, I'm coding them according to a diverging color scale, where you're now able to use your perceptual system to read off things like low values and high values and see distributions quite quickly without using a bunch of internal resources. The idea being that now you can actually ask higher level questions than just what's the range or the distribution. Now, one question is, why is it useful to actually represent all that data? After all, we've got statistics. Aren't we there? Aren't we done? Are we there yet? And the answer is typically that statistics is always necessary, but in many cases not sufficient. That sometimes the loss of information that you have in a summary matters, and the details are something that it would help if the person's able to see. And so part of what you want to do is confirm what you expected to see in the summary, but maybe look for unexpected patterns, or particularly back to this idea of model building. You want to gauge whether or not the particular statistical model you're using is actually a good fit with your data. So now in this room there's going to be some ringers, but I'm curious, who here has heard of Anscombe's quartet? Ah, many, but not all the people in the room. So this is this great example that was designed by the statistician Anscombe in the early 70s, where we have 4 data sets and they have identical mean and variance, x and y, xy correlation. So from this particular flavor of summary alone, you can't tell the difference. The instant I draw you a picture, of course, humans can tell the difference. We see a very classic distribution that's probably what you expected. We see something that's clearly nonlinear versus linear. You know, we see something where that regression line, that correlation line's a bit off. And then, of course, we see this nice, terrible example where it's deeply misleading. And this is, of course, a synthetic data set that was designed to mislead in that case. But the key thing here is you saw these patterns very quickly, and this is 20 data points. What happens when we have thousands or millions of data points? What happens when we have dynamic data that's changing over time? It just gets worse. So this is the opposite of it gets better. And so it gets worse. There's a lot of situations where we really do want to show people a lot of the details. And that's where visualization shines. Now, there's another interesting idea, which is that there's actually some resource limitations of 3 very different flavors. And computers and humans and displays all have their limits. Now, for those of you who came out of computer science, the idea that there's computational limits that we care about, like CPU time or system memory, this is obvious, and we are used to thinking about them as computer scientists. But there's also very different limits, even though some of these words are the same, for humans. And what it means to have limits of human memory are quite different than the limits of computer memory. Certainly Moore's law is not going to help us, but more to the point, it's a very different model where we have, particularly for things like short-term working memory, some really strict limits on what we can do, and particularly what we can attend to at once. Now, there's a third limit people might not have thought about quite as much, which is this idea that there is limits on the displays. So keep in mind, display technology has gotten better at a far slower pace than computer technology. And so one of the most precious things you have are pixels. It's what you run out of. Even before human attention, you start running out of pixels on your display. So it's useful to think about those as a constraint in your situation as a designer. And one thing that we struggle a lot with is this trade-off of information density. When are you encoding information versus having white space that's not telling you anything? And the reason it's tricky is that, of course, it's a trade-off. You don't simply want to put everything on the screen at once all on top of each other. That's too much clutter. But if you spread things out too much, then it takes huge amounts of navigation and zooming to even see anything at all, and it's hard to see details in the overview at the same time. So this idea that there's a trade-off of information density is one useful thing to think about. Now, finally, this definition has words like tasks and effectiveness in this. And this should immediately make you wonder, what does effectiveness mean? Is there an operational definition of that? And there's an idea that a lot of people have, which that Viz is intended to let you do new things you could never do before. And that's definitely one of the use cases of it. But it's not the only use case. Perhaps the even more common case is to speed up something people are doing already, but to do it dramatically faster. So there's both novel and fast. Now, what makes life both terrible and good is that this is hard. It turns out that most of the possible designs you could have for a Viz system don't work. They're ineffective. And so one of the arguments in my book of why I'm presenting things the way I do is that I want to increase the chances that people do good designs by having them think systematically about the entire space of possible designs. It's a large space. It's easy if you don't know much about Viz to get stuck in a very small part of that. And as I'll be talking, this idea is that, well, how would you know what to do? You're constrained by the tasks in addition to your data. So it's not totally surprising for people outside the field that your data set, well, has got to dictate something about how you show it. But keep in mind that there's many, many possible pictures of the same data set, and the task of what the user's trying to do is a way to actually try to constrain your choices as a designer. Because, as we'll talk about some today, representations of data don't all serve the same tasks equally. Some are better for some tasks and some for others, and likewise for the data. So the book is built around an analysis framework that thinks about 4 different levels and 3 different questions. So let me give you an overview of that. So in what I call the nested model of thinking about visualization design, I'm actually splitting things up into levels to help us think about them separately. So at what I think of as the very top level, the outside level, is a domain situation. There are some particular people you might have in mind to use a system. And they have characteristics. They have maybe particular domain knowledge. You know, they might be a physicist, they might be a chemist, they might be in finance. They will have particular data. So there's a lot of questions you can ask about who is trying to use this. And in some sense, this is a very classic HCI question of, you know, who are you designing for? And then there's something that's really important and perhaps far too easy to ignore, which is the idea that we need to abstract from some domain problem in domain language to something that we can actually reason about cross-domain. And so this idea that we need abstractions where we translate from the domain to generic is a really, really key question. And I'm going to focus on 2 different questions. One is, what is being shown? So I'm going to call that the data abstraction. And also, why is it being shown to the user? I'm going to think of that as the task abstraction. Now, this is a very interesting terrain because, first of all, there's this question of translation to something generic. And a lot of this talk will be the building blocks of a generic vocabulary for thinking about data and tasks. But in addition, what's particularly interesting about the data abstraction is you might do something different than what you're given. The easy case in visualization is someone hands you a data set and you draw a picture of that. The interesting case, which almost always happens with large, complex real-world data, is you're given a data set and then you do some series of transformations such that you derive new data so that when you draw the picture of that derived data, you actually help them with what they had in mind. And so this idea that your data abstraction is actually a design choice, not just what you're given, is one of the really interesting and hard parts. So really thinking about this abstraction layer explicitly as its own thing is something that I argue is a really good idea, and that we're thinking about the what and why at that level. And now finally, to move on to what you might have thought about as central to Viz, I'm calling this an idiom. A lot of people call it technique or method. And in particular, it's how is it shown? So how do we actually make these interactive visual representations? And I'm going to split that into what I'm going to call visual encoding. How is it that we draw these pictures? And interaction, which is how do you manipulate these pictures? And for some idioms, these are actually very intertwined and you can't easily separate them, but some fall more on one side or on the other. So I'll talk some about visual encoding and interaction. And one of the reasons I focused on this question of idiom as its own level is I want to separate out this question of designing how you draw and interact with the picture from the algorithm level, which is how do you instantiate that efficiently in some computational format. Because you can have different possible algorithms for the same idioms. And so it's useful to distinguish between them. One thing about these 4 different levels is anything you figure out at one level above actually cascades down. So decisions you make about abstractions cascade into idioms. Once you've specified your idiom, well, that dictates what your algorithm needs to do. So this idea of these nested dependencies is important. Now, one of the reasons that I find this model an interesting aid for thinking is it helps you answer the question of, did it work? How do you know if your design has actually succeeded? And the interesting thing is that Viz is this very highly interdisciplinary field where you need quite different methods to answer the question of, did I help, at every one of these levels. So let's actually start with that central level, the algorithm level. Well, that's something that as computer scientists we learn about, right? How do you run a computational benchmark? Interesting and tricky. Complexity analysis for those who are more theoretically inclined. So the methods of computer science serve us very well at that innermost box of algorithm. But there's a lot of questions that we can't answer that way. So questions like, do I actually have a way to draw this picture that works with human brains and processing? That tends to be something where we often want methods more out of, say, cognitive psychology. If you're actually running a controlled experiment in a lab with a stopwatch measuring human performance, there's a lot of trickiness to that experimental design that you are not taught in a typical CS class. And so a lot of issues about how do you do what I'll call lab study for short, controlled experiments, those are methods we often get out of cognitive psychology. And then how do you think about whether or not this thing that you've designed is even reasonable? So often there's a lot of design guidelines for these. So there's a lot of methodology out of design, generation of multiple alternatives, trying to justify some of your choices, the idea that there's not a single correct, perfect answer, but there's many possible good answers, and a giant number of terrible answers, and distinguishing between those is interesting. But actually, there's even more. So that whole question of the domain situation and the abstraction of translating from a domain problem into something generic, how do you know if you got that right? That's an interesting question that is not well served by controlled experiments in a lab. This is something where you actually want to get methods less out of cognitive psychology and much more out of domains like anthropology and ethnography, often as filtered through HCI. But often much more qualitative methods where you actually go, you talk to people, that's necessary but absolutely not sufficient. You often have to observe them. You can see what happens in a field study where you deploy your system to people and see whether what they can do changes and try to understand how that changes. That's typically not something where you're looking for statistical significance, but something where you're doing a very different methodological approach of trying to understand what's now possible or what is now sped up, but not so much with a stopwatch. Now, what's important about these divisions is one of the big areas of weak work in visualization is when people try to validate choices at one level with methods appropriate for another level. So in particular, if you're trying to convince me that people can use an idiom well, you're not going to convince me of that by telling me a CPU benchmark about how fast your algorithm was, because that's a different level of design. And likewise, I mentioned this idea that it's pretty hard to figure out the abstraction stuff with a user experiment. Why is that? Because in a controlled experiment in a lab, you tell the user what to do. If you're trying to figure out whether your understanding of what users do is correct, well, you're not going to succeed with that. So this approach to thinking about validation methods at each level is something that I found has really helped my own thinking and also helped me understand different aspects of this design. Let me emphasize one thing. This is not something where you start at the top and go all the way down to the bottom and declare victory. It's very, 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 very iterative, as with many design issues. Now, let me address this question of, so why am I talking about analyzing visualization systems so much? It's in the title of the book. Why is this? And I argue that analysis is a way to try to impose a structure on a very, very, very large design space. So it provides some kind of scaffolding to help people think in a systematic way about some of these design options. And my argument is that analyzing existing systems can be a useful stepping stone for a designer who wants to design a new one, because it gets them to think about the design space more generally. So let me actually give you a quick preview of this. Before I talk about the framework much at all, let me show you an example of comparing two systems which in some ways are very similar, and then in other ways are very different. right? If we just look at the pixels on the screen, well, they're doing pretty different things. So what's really going on here? Here's two systems for looking at large trees. Space tree is some work out of Maryland. Tree juxtaposer is some work out of our own lab. Now, if I use this why, what, how analysis system that I talked about, these questions of what are we doing with the data, why is the user doing it with the task, and how are we actually doing the idioms? Well, from the what point of view, well, they're both looking at tree data, all right? I'm positing that users are doing the same task in both situations. And that task is to try to find a path between two nodes. So out of all the possible paths in the tree, what is the one that we're looking for? And then that question of how. Now, notice how both space tree and tree juxtaposer are somehow visually encoding that data, right? There's a picture that we're drawing. That's pretty pervasive in all viz systems, is that we're visually encoding. They both have an interaction technique that involves some flavor of navigating, right? You change over time and as you zoom in. They both have this idea that you can select an object, but then there's a place where they differ. With space tree, once you select something, much of the rest of the tree is actually filtered out and parts are aggregated together. That's actually these aggregated things where, depending on what you've chosen, you see a lot of the rest of the tree in a very compact, simplified cartoon-style version. And tree juxtaposer does something very different. When you select something with tree juxtaposer, what it does is it changes the spatial arrangement of that layout. It's actually stretching and squishing. So it's stretching out part of it, compressing the rest. So these are different approaches at a high level, arranging in space versus aggregating and changing the visual representation to this same question. So a lot of my arguments with the analysis framework is to help us think in this quite systematic way about systems. So what is this framework I'm talking about? Well, there's a lot of stuff here. So let's start with this question of what. What are some ways we can think about our data in a generic way that's not tied to a particular domain? Now, I mentioned that there's a lot of book and a small number of minutes in this talk. So I am not going to slog through every detail in all of these diagrams. I'll be showing you a lot of big picture diagrams to give you a flavor. I'm just going to pick a few things out of this to give you a sense, a flavor of this kind of analysis. So in particular, I'm going to talk about this idea of data types and data set types. So I argue that in visualization, there's really three main types of data we have to worry about. And I'm going to start out with tables of data. That's a common case, right? You've got a spreadsheet. It's in Excel. What have you got in it? The vocabulary I'm going to use to talk about this is that in the really simple, nice, easy case where you've got a flat table, your items are your rows, your attributes are your columns. You can think about having some value in there. Now, of course, there can be more complex and interesting multidimensional tables. As a computer scientist, think about this as an array with multiple indices or keys, and looking at interesting slices of those tables or roll-ups is where a lot of the action is. But there's something I want to have you think about first, which is what's happening with these attributes. What is the type of data that you've got? Is it categorical? So is it something where you can tell the difference between things? There's apples and oranges and bananas, but that's really all you know. Or is there some intrinsic ordering of your data? The classic case is you've actually got something that's quantitative, where you've got the weights of things like your cat. So your cat could be 20 pounds, another cat could be 15 pounds, and you can do arithmetic and say there's a 5-pound difference between those cats, and that is a meaningful statement. There's also orderings where you can't do that kind of quantitative analysis on it. My favorite example is t-shirts. It is not defined what a large t-shirt minus a small t-shirt means. And yet, everybody will put the medium t-shirt in between the small and the large. So there's an ordering, but you can't actually do quantitative mathematics on it. So this question of do you have an ordered data attribute or something that's more of a category, we'll come back to very shortly as being a really central question. But tables are not the only kind of data. So another interesting thing we can think about explicitly is what if you've got a network? What if your items actually have some connections between them? In this case, we often call the items nodes, and we call these links between them links or edges. Sometimes these networks are called graphs. There's a field of graph drawing and visualization. I'm going to avoid the word graphs here and mostly try to use the word network. There's also a third type of data. And that data is where you have spatial information that's intrinsic to your data set. So this idea that you have tables or networks or spatial data is really what I think of as this holy trinity of the 3 data types in Viz. Now, there are flavors of spatial data. One is that you've actually got continuous data that you're sampling on a regular or an irregular grid. So if we think about this room, for example, we could think about sampling in many places in 3-dimensional space to get things like maybe the airflow, the temperature. And so suddenly we're dealing with some of the interesting mathematics of how do you sample continuous spatial data and interpolate. And so there's a lot of interesting implications once you start being in a regime where you're thinking about continuous data that you have samples of rather than more discrete data. And of course, you could represent spatial fields in a table, but I really want people to think about when is data spatial. There's even the case of where you simply have shape information. There's geometric structure. That might be points or lines or surfaces or volumes. So this question of tables versus networks versus spatial data is the way I think of a fundamental division. Natalie?
Where do you put time in there? Is it a specific quantitative, like the time attribute or the time dimension?
Yeah.
Is it a specific attribute then you're thinking, or?
Well, so this gets into the stuff where there's more complex stuff in the book that I wasn't going to go into deeply, but let me mention briefly. So the way I think of temporal data is, I wonder if I can skip forward. Yeah, no, the short answer is you can think, so time could be a key to your data, right? You could think of time as actually being one of the ways that you're indexing your data. Or time could be more of a value, right? So you might have something which is, I took this sample on Tuesday, that's time as a key. Or you might say there was a horse race and this race lasted 47 minutes, but that's not really something you're using as a key, that's more of a value. So time alone doesn't tell you whether the semantics are key or value semantics. And there's certainly a lot of data sets where you actually have both space and time, but there's a lot of non-spatial data where you also have time. So in some sense, I think of time as one of the keys that you could have. But in this kind of high-level, super high-level picture, it's not quite first class in the sense that it can be attached, it can be an attribute type for any of these. So it's important, but it's not a way to distinguish between. And if we have lots of time at the end, we can go deeper, but I'll keep going for now. So that was just a few little flavors of this question of what do we have? What are these building blocks of abstract data? Now, I'm going to spend a little bit more time on the why. This question of what is an abstract vocabulary of tasks that people have to do. And so, again, I'm not going to walk through absolutely every part of this, but I am asking you to notice, well, there's this column of actions, and there's this column of targets, and what's that all about? So a lot of things that people do are these action-target pairs. And so I'm thinking about that systematically. So if you start looking through visualization papers, you'll see a lot of these phrases like, the goal is to discover distribution, or to compare the trends, or find the outliers, browse topological structure. So this idea that there's an action and a target. So let me actually walk through in a little bit more detail what some of these actions and targets can be. So with the actions, there's really 3 separate levels where you can ask these questions. And they're actually decoupled, and they can go together in any way. So I'm going to walk through each of them separately. So one is this question of what are we doing at the analysis level when we're analyzing data? And already by that statement, I've made the world into the part I'm talking about and the part I'm not. So when I'm talking about analyzing data, that means specifically that I'm not addressing the use of data for artistic purposes. So I'm talking about the use of data for analysis much more than an evocative emotional experience, although there's some interesting areas about where those might overlap, but that's not what I'm focusing on today. So the really highest level split is, well, you could be consuming data that already exists. And a very classic distinction in visualization is this idea of discover something new versus present something known. I already even alluded to that in my previous slides. Sometimes that's called exploratory versus explanatory visualization, different vocabulary for that basic idea. And moreover, within discovery, there's often a distinction between verifying an existing hypothesis or generating a new hypothesis. Now, what's gotten a bit of press lately in the viz world is this idea of a third category that's still not so well understood. We've called it enjoy for now, which is people are having fun with their data and they're playing with it, and it's not their day job, and yet here they are. You know, it might be baseball statistics on the web or baby names, even if you're not about to name a baby, all kinds of things you might do with data. Sometimes that's called casual or social viz. So we have that as sort of a first-class citizen for you to think about as the goals of the user. Now, you might not just consume existing data, you might create new data as part of the visual analysis process. So we're calling that the case of produce. Now, one thing you might do is you might annotate, right? You might take the existing data set and add information to it. You might record an analysis session. Maybe you do that in order just to play it back later to show someone else to present. Maybe you do that to really make sure you've got provenance of what's happened with your data. The third one here is very, very crucial, and I want to put that front and center and get people thinking about it, because this is the idea that you might derive new data from your existing data. And I alluded to that as a crucial question in that data abstraction step. You can derive new things. You are not bound by what you're given. You're actually free to change that. And so I'll be alluding to this as we go along in the talk and point out examples where we've derived data along the way. So that's some questions we can ask at this, what I'll call the high level, the analysis level. There's some other questions we could ask for actions. One is, what does the user know? So words like search and explore and browse have all been used quite a bit in Viz. And we wanted to encourage people to think a bit more systematically about that. By saying, let's think about the target and the location of the knowledge. And so in particular, if you know what you're looking for and you know where it is, I'm going to call that lookup. In contrast, you might know what you're looking for, but you don't know where that is in the visualization. Let's call that locate. Now, there's the flip side of that, which is you don't exactly know what you're looking for, but you've identified a neighborhood that might actually be interesting. That's the location known. So let's think about that as browsing. And then finally, the somewhat terrible case where you don't really know what you're looking for and you don't know where it is, then you're really in what we're going to call exploration. I mean, this is both terrible and wonderful, of course. But by using this slightly more specific vocabulary, rather than just saying, oh, we're exploring, we find that that helps us think. There's one more question you can ask, which again is decoupled from these other two, which is how much stuff matters. Specifically, are they trying to identify one thing, right? That example I showed you before, you're finding a particular path. Or are you comparing a number of things to each other? So that's, you're looking at some of the data. Or are you actually trying to summarize all of the data? So this one versus some versus all, identify versus compare versus summarize. It turns out that a lot of what people are doing in Viz comes down to understanding which one of those scopes are you actually trying to build a tool for. And it's very common for people to realize that, oh, if I have to support the compare task, then all of the apparatus that I needed for identify is necessary but not sufficient, and we need to build something more in. And for summarizing the whole data set, well, suddenly that's actually the heart of what a lot of Viz is let's show people an overview. How do we do that? Well, that would be the devil in the details hard part. But this question of how to provide useful and meaningful summaries and overviews as the data sets grow bigger and bigger, maybe at multiple scales, is a really central question. So now this idea of targets. Well, there's some targets that actually have to do with any kind of data set whatsoever. So things like finding the trends or finding the outliers, that's generic to any kind of data set. Something I'm calling a feature is essentially any kind of domain-specific thing a user cares about that generically I'm just going to think of as a feature. Now, thinking about attributes in particular, a lot of core questions can be answered by thinking about one attribute all by itself. And one of the most common things in visualization is understand the distribution of values within the attribute, or the special case of looking at extremes like min and max. But there's some questions that are about relationships between multiple attributes. And so, for example, is one attribute dependent on another? Are they correlated? Are they similar? These are questions about multiple attributes, not just one. And there are also some targets that depend on the kind of data. So once we have network data where we've got relationships between items, suddenly we can ask questions about that topological structure of the network. And path tracing that I mentioned before is just one special case. And there's another really interesting one to think about, which is what are people doing with spatial data? Often understanding the shape of that. The geometric shape is the task in and of itself. And one of the reasons I emphasize that is there's many other tasks where understanding shape is not crucial. And so it's important to always understand whether or not the spatial shape of something is a central question. So that was our kind of whirlwind tour through the why. Now, in the time we have left, I'm going to talk about certain parts of this question of how. And really that's at the heart of the book is how do we encode this information and interact with it? And so there's a lot of choices. I'm not actually going to talk in great detail about the more understood parts. And that is this part on the left, how do we visually encode data? I'm going to talk about just a little bit of that to give you a glimmer, where a lot of the questions of visual encoding come down to the use of space. How are you arranging things in space? And then there's a number of other visual channels, including color and others, that we also use to communicate data visually. So just to step through the real basics of that, what if I have this question of, so I've got some visualization idiom, how can I analyze this? And it starts at the level of saying marks and channels. So let me give you that vocabulary. What I'm going to call a mark, a geometric primitive, is a way to, and some mark has meaning. It might be a point, it might be a line or a curve, it might be an area. Think of these as geometric primitives. And now the interesting part is what can we do with the geometric primitives? We can control their appearance through these things I'm going to call visual channels. And spatial position is a really central one. So it could be just horizontal or vertical or the combination of both together. We could color code, we could shape code, we could have orientation or angle or tilt. We can size code things one-dimensionally with length, two-dimensionally with area, three-dimensionally with volume. So here's all these ways to control the appearance of one of these marks in a way to communicate data about attributes to users. And once we have this idea of marks and channels, well, then we can start to actually analyze things. I'm picking these very, very simple examples just to walk us through. What can we say about a bar chart? Well, it's encoding using vertical position a mark that is a line. What about a scatter plot? Now we're actually encoding two different attributes, vertical and horizontal, and we've switched from a line mark to a point mark. Then we can start to add more channels. We can say, once we add the channel of color, now we can encode a third attribute. And then once we add a fourth channel of size, now we can encode a fourth attribute. So these are simple examples, but they give us a vocabulary. Now, an interesting question is, well, how many channels are there? And the answer is quite a few. And so what's happening here? Here's a lot of these channels I already mentioned. I seem to have them in particular orders. What's going on here? This gets into one of the fundamental questions. This was actually originally proposed back in the 80s by Jock McKinley, this principle of expressiveness. And there's a crucial idea, which is some of these visual channels intrinsically to human brains communicate magnitude information. They should be used to show ordered attributes. And so this question of how much, that's something where if your brain is thinking how much in a channel, you want to make sure that you're encoding data that has an ordering to it. Because the flip side is there are also some channels that don't communicate magnitudes. I'm calling these the identity channels. They're saying this is something or it's not something. And these are a good match for categorical attributes. So what region is it in? What color is it? What direction is it moving in? What's the shape? As opposed to, how much? How long is it? How saturated is it? How dark is it? So these how much versus these what questions, these magnitude versus identities, this is the part you really want to make sure you have a match. If you show unordered data with an ordered channel, you're going to communicate something that's not there. If you communicate ordered data with this non-ordered channel, you've lost information. So that's one important principle of matching up those characteristics. The other point is there's actually a spectrum here of effectiveness, where we're going from the most highly effective at the top to the least effective on the bottom. And you want to try to understand, if you've got multiple attributes in your data sets, and code the important ones with these higher ranked channels. Now, an obvious question you might ask is, where did these rankings come from? And how can we actually use them? And let's actually think, if we wanted to have lots of extra time, like if we say had an extra hour today, I would go much more deeply into these questions of justifying these rankings, talking about where they came from, and actually walking you through a lot of these choices for using space and color and the other channels. But that's actually not what I'm going to do today. So this is, I would argue, the part of visualization that is more well understood, that has had a lot more camera time. And although I think there's a lot of interesting stuff in the book that's a somewhat different way to think about arranging space in particular, through this lens of either expressing quantitative values, or this idea of separating it out into regions that you order and align, or just use given spatial data, that to really discuss this is something I can't do, and also talk about these at the same time. So I'm not going to go deep into these questions of space and color and other channels. Instead, today, I actually want to focus more on this question, not just of how you draw the picture, but a systematic way to think about the ways you might manipulate that picture. So in the time I have left today, I'll focus on that. Just with the caveat that there's a lot of other stuff going on with space and other channels, but time is finite. So the part I want people to think about is this question of, if your data set's really simple, like those tiny little scatter plots and bar charts I showed you, well, you draw the whole thing. What happens as your data sets get bigger and as they're dynamic? How do we handle complexity? And what I'm arguing is it's useful to think about essentially all the techniques we have in visualization as fitting into one of 4 different strategies. So the 3 that I haven't talked about yet are this idea of manipulating and faceting and reducing. And the one I already have talked about is the idea of deriving new data. So a classic example would be, you could have 2 different line charts. You could draw them both and make the user actually think about what the difference between them is. That's actually this more cognitive act. If you can just derive the difference between them and show that directly, you could visually encode exactly what they need to know. That's a simple case of deriving. But it's something that we're going to, as I mentioned, be using all through a lot of the examples. These other 3 approaches to handling complexity, well, one is this idea of manipulation. You're changing something over time. You've got some view you're looking at data in, and you can change it. A special case even of that is to navigate or to select. So these are all things about having a view that changes. Now, there's another set of choices that has to do with saying, I could have more than one view at the same time. So a lot of design choices about faceting your data across multiple views. And then finally, a suite of choices of saying, well, within a single view, how do I reduce the complexity? I might filter stuff out, I might aggregate it, I might do complex combinations of that. So these 3 design choices, plus that 4th one of derive, are the ones I'm going to focus on a bit today, with just a few examples. So let's start out with this idea of manipulate. And in particular, having a view that changes over time, well, that's actually obvious, right? That's what most people would just sort of bring to the table and say, well, I could navigate, I could zoom, I could pan, I could change stuff. So that has a lot of power, and it's also extremely flexible. So let me show you just one example of that. An idiom that's used a lot in visualization is this idea that you'd have an animated transition from one state to another. Well, why is this? It actually gives you some support for seeing how one configuration changes into another, where you don't have to, for each item, separately try to figure out, well, where did that go? Where did that go? So it's an alternative to a jump cut, which has relatively high cognitive load. And as long as there's not too much changing in between these 2 views, and you can actually have items smoothly move between, you have a much better ability to track. So this particular example is looking at a multi-level matrix. So here's where we start out. We see a few snapshots of it to its next state. And what we're doing is the user's actually selected this part in the middle, and that's now getting gradually expanded larger and larger to a final state here. And if you just had a jump cut, time for a laser beam, if you just jump cut from here to there, it might be very hard to track, that the fact that this square here now became that square there, whereas actually having these intermediate views where you're gradually increasing the size of one and fading out to the other is a way to support the user's ability to track between these. So this is just one example of change over time. There's a huge amount that people do, particularly things like zooming and panning, that all fit into this category of something changes. Now let's contrast that with some of these other choices. So you might say, well, instead of just having a single view that changes over time, maybe I'll have multiple views. Now, let me point out, actually, just briefly going back, all of 4 of these choices are often all done at the same time. So it's not that if you pick one, you can't do the others. In fact, it's extremely common to combine them. But for the purposes of analysis, I'm going to think about them separately. So this idea of faceting across multiple views. Well, what are some things we could do? We could have multiple views side by side. We could think about how it is that we chop up the data between the views. And we can think even of putting 2 layers on top of each other. So let's start with this question of, if you were to use multiple views side by side, how can you do that? What are your design choices? Well, one question you can say is, am I going to visually encode the data the same way across the views or differently? And particularly if you've got different encodings, it can be very interesting to say, and if I highlight a section in one view, how does that correspond in another? Another way to think about this is, are the views actually showing the same data? Or is one view a subset of the other? Or are they showing completely different data? And finally, you could actually also share navigation between the views. You could have linked navigation where navigating in one causes things to move in the other, or not. So, wait. Sorry about that. So, yes, we are, slides were not quite in the order I thought they were, but that's all right. So jumping forward to this idea of linked highlighting, let's actually see an example. A crucial question in linked highlighting, which is perhaps the most common interactive visualization idiom out there. And it's common because it's powerful and it's flexible. So the key question is, how is a region that's contiguous in one view distributed within another? So here's an example from baseball statistics, where what they've done is we've got a number of different views. So this is actually an example of a multi-form visual encoding where you've got some different views. We've got scatter plots, we've got bar charts, we've got these histograms, and the data is shared between them. So different ways to encode the data, but every view is actually showing you all of that same data set. So what happens when you actually select the high salary players, this is log scale salary, the question is, do the guys getting the big bucks, how are they distributed? Well, they're really distributed across different seniorities, and they're pretty distributed across the positions, and even about this question of, are you actually getting people out? But they seem to actually be clustered on the high side of the number of hits people have per year. So, well, okay, we're rewarding the people with a lot of hits with the big money. That seems kind of plausible. What about another way to look at the data? In this view, what they've done is they selected, there seems like this interestingly bimodal distribution of people that actually get a lot of the other people out. And this is distributed across salary and across years and across the hits, but we see that it's very much segmented into specific positions, right? Specific people end up tagging people out in baseball. That's how the game is structured. So this is just one example of this idea that linked highlighting can show you relationships between these different visual encodings in a way that gives you a lot of power. What's another way to think about juxtaposing views side by side? Well, a very different idiom in this case is these bird's eye maps. So these are pretty pervasive. Actually, at the moment, Google Maps has now taken it out of their system, but it's still quite common of having these geographic maps where you've got a detail view and an overview. And in this case, what we've got is the same visual encoding. These are actually both geographic views, but you've got a subset of the data, right? What we've done is here's our detail view and here's our overview. So we're seeing more in one view than in the other. And in many cases, you do have this bidirectional linked navigation. And so this idiom of having an overview and a detail together is extremely common, another way to get power. Now, a third flavor of idiom, the buzzword for this is small multiples, is where you have the same visual encoding in multiple views and showing different parts of the data, so typically disjoint sets of the data. So in this example, and this is one that you actually saw earlier, where we were looking at this gene expression data, at different time points in experimental conditions, we've actually got these completely different colorings of the same fundamental base layout of the graph. And again, this one's got shared navigation. So when we start thinking about these possibilities, there's a way you can think about this as a 3x2 matrix. And what's interesting about this is only 4 of those 6 possibilities are really very interesting. So if you think about your choices of do you show all or some or none of the data in common between the views, and are you encoding it the same or different between the views, well, then what do we have? Well, if it's the same encoding and it's the same data, that's just redundant and there's no point. The interesting cases are this one where you might have different encodings of all of the data, or these sort of overview detail you can do either with the same encoding or with different encoding. These are both extremely common. And then this case that the buzzword is small multiples is where you really have the same encoding across different partitioned disjoint data sets. And the thing I want you to notice is this cell is also boring. This cell is if you've got different encodings and none of the data is shared, you can't actually link the views. So that's not such an interesting case. Now, the point I want to make here is why would we do this? We already talked about the idea that you could just have a single view that changes over time. What is the benefit of having these multiple side-by-side views? And there's a section of the book, there's a whole chapter on rules of thumb that talks about sort of cross-cutting, interarching themes. And one of them is eyes beat memory. And so to unpack that, anything you can do with a human's eyes is much better than relying on their internal memory. And so the thing is, there's a lower cognitive load for this kind of side-by-side view compared to a single changing view, because it's easier for you to move your eyes between views and compare them in that way than to remember in your head what you saw before and compare that to what you're seeing now. So if this is so great, why do we ever do anything else? Well, there's a cost. Just like superpowers, with great powers come great costs. So yes, you're lowering the cognitive load, but you've just used up pixels. And you have finite display area. So there's a very finite number of views that you can actually fit before each one of them becomes so small that you can't see anything at all. So this trade-off between the costs in pixels and the benefits of scaffolding your memory is one of the core things that you then struggle with as a viz designer. But it's useful to think about that very explicitly. So there's some other questions. How do we partition into views? So I've said we have multiple side-by-side views. Well, how do we chop things up between them? How do we divide the data between these views? And let me point out something explicitly that might sound obvious and trivial, but I think is actually a really important and central question. What are you doing when you divide data between views? You're encoding the association between items with spatial proximity, right? You're saying, here's one view, here's the other. And it turns out that back to the way human brains work, this spatial proximity is a very, very, very strong signal to your brain that things are associated with each other. And so it turns out that by partitioning into views and having different regions and making choices about which items go into which regions, that is one of the most crucial questions in how you're able to detect patterns. So this choice of partitioning is actually very, very central. So how might we do that? Well, one thing we could do is say we could split according to attributes. Typically, we're doing this in situations where we don't just have one attribute. We often have many. We have multi-attribute tables that we're splitting in various interesting ways. So there's a whole lot of design choices. I'm not going to go into the design choices for all of the things, but just to give you an example that for every one of these design possibilities I've talked about, in the book it goes into much more detail about the set of choices. For example, how many splits do you do? Do you go all the way down until where you've got a single mark per region like you do with a simple bar chart? Or do you actually end up going part of the way down where you're doing some partitioning and then you've got a region that actually has quite a bit of interesting structure within it? Then you might draw something as a more complex glyph made of multiple simple marks. And so this whole question of when do you show things as glyphs versus when do you show things as marks, this comes down to how did you partition the data. What is the order that you split things in? As we'll see, it's got a big consequence. How many views? Open research question. Nobody knows. At least 2, not 6,000. In fact, not even 100. In fact, probably not even more than a few dozen. Is a few dozen completely pushing it or very viable? Depends on your circumstance. So this question of how many views is definitely an interesting open problem. So let me give a concrete example. Let's think about the bar chart case, because that's easy to think about. And what do we see that's different with 2 different partitioning choices? So if we start out with a table of data, and the first thing we do is split. So I've got a data set where I've got a demographic attribute, and I've got it by states in the US. So if I first split this by the state, and then stop, and say, OK, I have one region per state, now what? Now I've got these multiple attributes within each region that I want to visually encode. In this case, I'm going to do it where each one of them has their own bar. So this is basically a grouped bar chart. So what's the point here? It's really easy to make comparisons within a state. We can think, how do the demographics of California work? Oh, look, there's this dip in the middle, and then it spikes way up. And is that different or the same from the patterns in these other states? So you can make comparisons within the state. It's easy, but it's kind of hard to compare, how many people are that middle demographic group because there's all this stuff in between. In contrast, you could split the other way. You could say, first I'm going to split by age. And within each of those regions, what am I going to do? Well, actually now I could just have one chart in each region. I can have a single bar chart per the region. What can I do now? I can very easily compare across age. I can say, oh, this is relatively flat, whereas this one's actually descending. So comparisons now within age are easier, but across states is harder. So by making a choice about partitioning, we have dictated what kinds of visual patterns are easy to see versus hard to see. And this is easy to understand with bar charts, but things can get more complex as you combine these with some of the other more exotic layouts. So let's just look at a few other examples. Here's a data set called HIVE from the folks at the GI Center, and they've got a data set where they have housing sales in London. So the kind of house, the neighborhood it was in, and exactly when it was sold. So first, let's think about, well, what's one way to look at this data? In this case, rather than just looking at it as a list of things or even a matrix, we're actually recursively subdividing. So this is part of the discussion about spatial layouts that I'm not going to get deep into, but I'll just mention this as an example of this relatively complex recursive subdivision structure. So what they've done here is they first split it by the type of the house. It's an apartment, a flat, semi-detached, a terraced house, a completely detached house with a yard, like a lot of folks have out here. Then they split by neighborhood. So these are a bunch of the neighborhoods within London, each of which is in its own little box. And then they've got time where the rows are the years and the columns are the months, so you can start to see some temporal patterns. Now, what you can see in this view is allowing you to very easily look at things like what's happening within a neighborhood. Let me compare one neighborhood to another. This one's much darker, meaning the house is sold for higher prices. So you can start to immediately see things like, well, which ones are the rich neighborhoods? Which ones are the poorer neighborhoods? Which ones don't have actually very many houses at all being sold? So what you see in this view is different than if we partition the other way. What if instead we say, first I'm going to split by neighborhood, and then I'm going to split by the type of the house? Now you can see very different patterns. Now it's much easier to say, I see, some of these neighborhoods are actually dominated by one house type versus another. And we can certainly see things like, I see, certain types are in fact more expensive, right? The detached houses in general tend to cost more than the apartments. So there's some analysis of these other categories that are easier to see because we did a different partition. Now, just to wrap up this example, partitioning is not just for rectangles and squares. Here's an example where first they partitioned into the house type, and then they said, okay, within that, now let's actually encode the data where we use spatial information. So in this case, instead of just having little squares and rectangles, we're actually saying, let's show the geographic boundaries, and we'll still color code by the attribute. Technically, that's called a choropleth map. And so the point is, there's many ways of visually encoding the data within these regions, and some of those choices are very interesting and central as we think about partitioning into views. Now, I'm not going to go deeper on this front. I'm going to come back again to this question of we've now talked about a changing view, we've talked about partitioning into multiple views. I'm just going to briefly talk about this idea of reducing the amount of data that you show in a single view. So what's the idea here? Well, first let me mention when I talk about reducing the amount of data, well, half the time I actually mean increasing, right? So these are these inverse things. You can reduce, you can increase. So these are ways to throttle the amount of information you have. Now, a core choice is to filter, right? Filter means some stuff you simply don't show. What's nice about this is, first of all, incredibly easy to explain to people, and often computationally very nice and straightforward, and suddenly you've dramatically reduced the size of your data set, and everything is great, and life is fantastic, and so why don't we just do this all the time? And the answer is, this gets back to how human brains are. We have this terrible tendency to have out of sight, out of mind, not just be a proverb, but actually a reality of how we visually process data. Even if you yourself hit the filter button 3 minutes ago to stop drawing things, you immediately start drawing conclusions as if what's hidden doesn't even exist. And it's so built in that it's really hard to avoid that. So even though filtering is very straightforward, it can really end up with you being misleading if you just don't show some of the data. Well, what's the alternative? Aggregation is a more complex thing, where what you say is, I'm still drawing a smaller set of things than my original, but rather than just completely ignoring some of them, I'm actually going to say I've got a proxy item that stands for a number of original items. And so what's nice is that proxy item, in a perfect world, informs you something about the entire set that it replaces. But how do we do these proxies? Oh, well, that would be the hard part. So how do you build these aggregate proxies in a way that doesn't lose all the signal you were trying to encode? So it's very well known that if, for example, you just start averaging things, you can easily smooth out the interesting signal in your data. So a lot of interesting questions come to doing something more sophisticated. Often with aggregation and filtering both, you're doing something interactive where you're changing over time. So a lot of interesting visualization design choices come down to combinations of filtering and aggregation, either statically or dynamically. And let me mention, you can do this either for items or for attributes. So either the dimensions, the attributes that you're showing, or the items that you're showing. And again, I really want to emphasize what's very common is to combine these things. In fact, the technique, the so-called focus plus context techniques, where you're embedding focus and context information together, are really sophisticated combinations of filtering and aggregation. And so not only can you combine filtering and aggregation, but those 4 major design choices of reducing and faceting and changing and deriving, these are all things that are typically combined. So let me show you an example of, in this case, a well-known static aggregation technique, the box plot. So I want to walk you through that just to put this into context. This is designed for the task of finding distributions. And you start out with some table of data. And then what do? You do something interesting, which is it doesn't matter how big that table was. We are aggregating that into a very small number of numbers that we can then show visually. So we're visually encoding the derived data of 5 quantitative attributes that actually express a statistical summary of that original attribute. So of course what we've got is this central line showing the median. You can see these upper and lower quartiles explicitly encoded as the height of the box, and then showing the points beyond which things are outliers, and if there are outliers, sometimes explicitly showing those. So this is an example of a static aggregation technique. A lot of the interesting action comes when we start doing things that are more interactive and dynamic. Let me, just to give you the other side of the fence, show you a particularly complex example of aggregation. This idea that actually we might aggregate not just items, but we could aggregate the attributes themselves. Think of these as dimensions of data. So here's an idea of a pretty complex idiom and task of how do you look at a huge document collection? What do we do now? Well, documents weren't even in our set of data that we knew how to encode. You know, you've got free-form text. What do you do? So first of all, a very common transformation is turn the document into a table. Well, how could you make a table out of a document? You could say for each word in the document, I'm going to think of that as an attribute and actually just keep a count of the number of times the word appears in the documents, the so-called bag of words model. That's a row in this table, and then I have 1 row for each of these documents. What do I have? A really big table. And looking at that table directly is not very interesting. It's incredibly sparse, and it doesn't help the human do much. But now what could we do? We could say, well, I'm going to take that very large table, and I want to derive a much smaller table that has only 2 attributes, 2 dimensions. So that is attribute aggregation. Now, the question of how we do that, many algorithmic papers. It's an interesting topic. That's a whole nother hour-long talk, which we won't be doing today. Lots of fun algorithmic meat in there. But let's posit for a moment that we found some way to actually not lose too much of the signal because we assumed that there's latent structure in the data that was gathered verbosely, so it's reasonable to actually throw away quite a lot of redundant information. And now what do? Now suddenly we have points in 2-dimensional space instead of points in high-dimensional space. What we can do is start to use a visual encoding like drawing a scatter plot to look for clusters. So now our task is to say, oh, are there documents that are relatively similar to each other? So dimensionality reduction is a hypothesis about, is this an interesting space to look at? Then you can look at the documents themselves and try to see, do I see clusters? Do I believe the clusters I see? You might actually do a lot of exploration and navigation to go in and actually select, this point represents a document. Maybe you read that document. You might try to say, all right, what is this cluster even about? Is there a way I could come up with a label for that cluster that's meaningful? So the thing to notice here is I've actually structured this as 3 cascading tasks. So when I mention this idea that you want to analyze things in terms of tasks, sometimes you actually want to think about sequences of tasks, not just a simple task in and of itself. Most interesting complex visualization systems handle these sequences of tasks. And a lot of this question of the indeterminacy of the analysis question. At the beginning, I started out by saying, what if people don't know what they're asking? Often sequences of tasks clustered together are a way to actually go back and forth between a lot of different possible questions. So in this one, I've framed it as 3 different tasks where the output of one is the input to the next. So it's really focusing on deriving data along the way. And so this is an example of quite complex attribute aggregation. Now, this was a whirlwind tour through a subset of what the entire book goes into in more detail. So I introduced these ideas of the 4 levels, domain and abstraction and idiom and algorithm. I introduced this idea that there are these 3 questions you can frame. 2 of them are the abstraction level, the what and the why. The how is at this idiom level. I haven't talked at all about algorithms, except to allude to the fact that they're fun and we want to do a lot of them. But that would be another 17 hours of talking. In fact, the book itself does not get into the algorithm level. The book itself is staying mostly at the abstraction and the idiom level in order to make it 400 pages rather than 4,000 pages. So speaking of lots of detail, we saw briefly this idea that there's this typology of what questions, typology of why questions. There's a lot of how questions. We just alluded to some of them. If folks are curious, as I mentioned, there is this book. It goes into a lot more detail. If people actually feel like getting the ebook and the book together for less, this is a magic promo code that will work on the publisher's page. The talk slides themselves are also on the web. Let me mention that all these diagrams I have, if people want to use them in their own talks, are available as Creative Commons licensed, and Emin McGuire did a fantastic job with those. And finally, there's a lot more information about all the other stuff we do, actually my own research, which I didn't talk about very much at all, both on our group's page and then my own personal page. So with that, I am going to switch over from talking at you to getting more questions from you, either those of you in this room or on the screen. And aha, I see there's a question from a long time ago. So let me start with this poor question that has been languishing on my screen, forgotten, from Conan Yang. Sorry about that. I'm not used to having questions come in through this modality. So your question was not sure why the display limit is the most constrained resource. And so that was actually way back on slide 2, I think, or something like. Yeah, so what I would argue is typically you've got quite a lot of computer memory to play around with. And even the humans have a fair amount of resources, but often what we end up with is a situation as a designer where the first thing that causes you pain and agony and swearing is that you've run out of pixels. You can partially address this by saying, let's add more displays. And these days, in fact, a lot of people do at least have one high-res display or even a couple of high-res displays. You can even have more complex things like display walls, but then you start getting into the constraints of how much of that can you actually attend to in high resolution at once. So
it interoperates with human attention as well.
Yes. But basically, and one reason I kind of emphasize this a bit more is that it's the resource that I think people tend to think about the least. People are used to thinking about computational resources, and at least people with an HCI background are used to thinking about human limitations. But thinking about the pixels as something in and of itself, particularly when you start thinking about the multiple displays. And so then when I started talking about these issues of faceting, where every time you add a new window, you take away the pixels available for the other windows, it helps to think about that really explicitly as a trade-off of a finite resource. Any questions for people in this room? Yes, all the way in back.
So I just want to get some insights from you. when you're using multiple encoding channels to design visualization. So I remember I read somewhere, I forgot actually specific which book. So there's two perceptual structures from psychology, integral and separable.
Yes.
So integral means that the two characteristics are perceived more integrally with the human brain, such as X position and Y position, and lightness and saturation, etc. And separable means, for example, size and color. There are two different encodings, and when people perceive them, they turn to be separative. So, once again, what's your insights on that? So, when you're using those multiple channels, mapping those multiple channels to multiple data attributes, because you have so many design choices.
Yeah, let me actually bring up the relevant slide for that, which I had to remember where I've put it, but I believe I've got it here. Yeah, so this question of separability versus integrality is this sort of interesting and complex one. So, right, because I had this whole table of channels, and then the question was, when are you allowed to say, I can combine this channel and have them actually read off the information separately, versus when is life not so good? And so this is the place where there's actually been quite a bit of study in the cognitive psychology literature on human vision. And so some of this is understood, but there's still a lot of frontiers where it's not fully understood. But let me just actually walk through this example because I think it's evocative, where, for example, spatial position and the hue aspect of color are very, very separable. So what we can do is we can say, what I've done here is I've got basically two groups of two. There are two groups spatially, right? There's this group versus that group. And so that's one attribute having two possibilities. And I've also got another attribute where I'm coding by blue or by red. And so you are able to selectively attend to either one of these. You can either attend to position or you can attend to color. So that means I've successfully encoded all of that information here. But things then start getting worse, right? Here's a situation where it's really easy to tell apart the big purple circles from the big blue circles, but it's a little harder. When I have size coding, size interacts with color, such that it's harder to tell apart. It's not impossible, but it's harder to tell apart the small purple circles from the small blue circles. You've sort of got less dynamic range in which to make that perceptual discrimination. But so there's a little bit of interference, but at least we're still able to see that there are two groups. There's little stuff and big stuff, and there's purple stuff and blue stuff. Now, what about here? Here's where life starts getting worse. Because what I've done is I've tried to separately use horizontal length and vertical length to encode information. And that sounds good if you just think, well, there's two different attributes, I'm encoding them with two different things. But it turns out that our brains are doing something integral with this. And what we end up perceiving is area. And so the problem is what we really see is small stuff, big stuff, and flattened stuff, kind of independent of whether it's flattened this way or flattened that way. So fundamentally, we're really seeing three groups of things, more so than the four we originally had in mind. So you can, if you try hard, actually start to say, okay, well, I'll try to treat these differently from these. So you can sort of start to recover, but it's harder. Here's a terrible situation where what I've done is, and I can tell you I've done this, and it doesn't help. I can tell you that there are two values of the red channel, and there are two values of the green channel. And I can tell you this till my face turns blue. And it doesn't help you actually see those because this color is actually perceived as a single perception. So you can't actually separate that out. You can't find the two values of red versus the two values of green. You just really do see these four different colors. And so even if you try hard consciously, you can't pull apart those integrated dimensions. So in general, one issue is understanding what the relationships are between the channels. So one of the things I do is talk a bit in the book about which ones are more separable and which ones are more integral. Basically, it turns out size coding ends up interfering with a lot of the other channels, and it particularly interferes with color perception. So that's something to be aware of. So the usual case in Viz is that you're going for this kind of experience where you want things to be as separable as possible. Sometimes you are deliberately going for this where you're actually getting this integrated perception, particularly in designing glyphs where you have multiple marks in a small region. So you want to be aware of this phenomenon. There is no magic answer, but understanding, and what we could use much more research on is, for example, let me go back to a list of these channels. Some pairs have been explored and understood, and others not so much. So there's been some work, Lynn Bartram, Colin Ware have done some work, for example, on the motion channels. Right now, it turns out that any kind of motion versus something static really, really strongly pops out at people. So you'll notice if something is moving around. It's conjectured to be unlikely by people like Stephen Frankenary that you can have multiple motion channels that are easy to disambiguate. So maybe it's not a good idea to try to say, well, I'm encoding one thing in flicker frequency and another thing in direction of motion, and a third thing in, like that probably is not very separable. But this is something which is literally not yet extremely well understood. So some characterizations, also like size coding interferes with shape coding. As things get smaller, you're less and less able to see. So there is some work, but it's not completely understood. So good question, longish answer.
This is an observation, not a question, but you're referring to the size coding interfering with color, and it seems that that's an example where that interference is true. We can all intuitively grasp that, but it's primarily true on very small sizes in that case, right? So there might be a large range over which they don't interfere much, but then other parts of the continuum, if you will, where there would be interference, and that may be true as well for other angular displacement or other things too. But it's kind of an interesting angle, like over what domain or what range do these things coexist very nicely, very orthogonal, and then at some point they don't.
Right, and so that's definitely, in fact, part of what I didn't have time to get into deeply with talking about these is you can think about these channels in terms of many things. One is the accuracy at which you can perceive things. Another is the discriminability. How many bins within each of these do you have? And so you can imagine a situation where, depending on the size coding, you might have the full range of bins or fewer bins. Also, the ability of something to actually visually pop out pre-attentively without conscious control. So these are all ways you can think about these channels. And so, for example, I didn't have time to go deep into questions of color today, although it's a pretty glorious topic. One reason color is so difficult for people to think about, first of all, is that some aspects of it are categorical and some are magnitude. So that's one source of confusion right there. And for example, there's definitely some overlap between things like saturation coding and luminance coding, where at some point, as you remove more and more of the hue, suddenly you start to be unable to distinguish. So there's a lot of stuff about color that also involves stuff that you wish would be separable that ends up being far more integral than you realize. Transparency also. In order to create visual layers, you often have a foreground versus a background, and you might have a semi-transparent background. It turns out that heavily interferes with things like luminance and saturation coding. So there's a lot of stuff involving color where it really very much comes to the forefront. Natalie?
So lots of what you presented, even though it seemed like you make it designed for exploration and presentation, right? But in my head, I was kind of thinking, okay, all of this technique or different methods to like juxtapose things or manipulate things, they're actually you couldn't say one is better than the other in many exploration cases. But then I started thinking, in fact, when you're in the presentation case, where in fact using pre-attentive things or maybe repeating things, or then that may become now some of them are better than others. So I was just wondering how much you thought about. So first, are all of those thought about the exploration and how you divide all of those different things and elements? Did you think really about those two cases, presentation and exploration, or maybe more one? And then also, do you have some sort of idea about if we talked about visual communication now, if some would be preferable or not.
Yeah, let me actually bring back a different slide to make a particular point. So one point is that these questions, of when is something good, I heavily emphasize that you can never say when is something good. You always have to say when is something good for a particular task and data abstraction combination. So I feel like a lot of the interesting questions come down to characterizing design choices at the how level with respect to specific configurations of what and why. And so it's never, is this better? It's always, is this better for this task? And so what you talked about was, wait, here are two very different high-level tasks, discover versus present. And so now can we start to characterize some design choices with respect to these tasks? And my answer is absolutely. Like the answer to almost everything in Viz is depends on the task. And so, but that's a good thing, not a bad thing. So this question of, so absolutely it could depend on discover versus present. In fact, it could depend on things even at a much finer level of granularity than that. I feel like one of the most interesting frontiers in Viz right now is basically, sort of we've done a lot of enumeration of blocks. Like if you think about these as, idioms as Lego bricks. The beginning years of Viz were all about, look at my new Lego brick, isn't it great? And here it is. And then at some point we became interested in questions of, and so what is it good for? Can we characterize not just this new brick, but a whole family of bricks as being related in an interesting way, in a way that we can tie to these questions of why and what. So I feel like these characterization guidelines for abstraction level into idiom level mappings is where a lot of these interesting questions are. So some of that work has been done, and there's just this enormous amount left to do. So it's kind of a long-winded answer, but my answer is yes, yes, yes. Absolutely, it depends, and not just on that, but on all the tasks. And so, I feel like filling in this, giant cookbook in the sky of, one day will we be able to write the Viz cookbook, where you say, this is my data and this is my task, and we have the complete vocabulary of these abstractions. So we've found a bunch of the Lego building blocks at this level, and we flip through and we find, page 5,673 says, okay, so for those, here are some sets of idioms that are known to be good or known to be bad. That's, the 30-year research agenda for the field. So, but we totally need to do it. Benjamin.
Regarding the limits that you said, so computational limitation, display limitation, and human memory limitation. So I was wondering, do you consider interaction as a limitation or as a limit for visualization? Like, is it out of scope of your model, or how does it relate? Can we solve everything with visualization, with interaction that we can't solve with the display, maybe?
I think of interaction not as a limit, but as a strategy, as a tactic. And so a lot of the really, many of the interesting Viz idioms are just intrinsically these combinations of visual encoding and interaction. With fisheye, like what is the encoding part, what is the interaction part? They're linked. So I feel like interaction is part of the strategies about how we do things. So a whole bunch of the design choices come down to specific uses of interaction. So it's not so much that interaction is a limit. Interaction is a technique to address a limit, which is human abilities to do things like remember. Interaction is very much a double-edged sword, because actually, to go back to this bits here, so the thing about interaction is anytime you're changing the view over time, you're now basically imposing a memory cost. You're asking people to remember, what did I do before? With a lot of navigation, the problem is, so I navigated and now I'm lost. Where am I? Where is the route? Where is home? And so a huge amount of the techniques that we propose are ways to basically scaffold the frailties of human memory to get some of the power of interaction. Because the power of interaction is you, the Viz designer, didn't have to figure everything out a priori. The user is allowed to actually do a bunch of this exploration. But then you're actually now taxing their cognitive system more and more. So there's this sort of trade-off of power versus cost. So I think of all the interaction techniques as being sort of a part of this system of design choices where, in some sense, I mean, one of my logics behind this taxonomy the way it is to say, so let's explicitly think about stuff that involves changing something, which is at the heart of interaction, but a huge amount of the power of all of these side-by-side views is the fact that you interact with them, right? So as you go in and you select an object in one view and see it highlighted in the other, well, that's a combination of linking views and interacting. And so a lot of these reduction techniques of filtering and aggregation, you know, the simple ones are all static. The interesting and complicated ones, of course, are all dynamic, where as you interact, as you select things, as you do things like, well, let me select a scale at which to aggregate in this local region. So to me, it feels like that interaction is essentially a suite of design choices that work in combination with these others to actually give you a lot of power of the viz. Again, sort of a long-winded answer, but.
Maybe I have a last one. How confident are you that you've covered everything that can exist?
So, the answer is,
Should we launch a challenge there?
yeah. So, the answer is, in some ways, I am reasonably confident, and in other ways, I am absolutely sure that it's incomplete. So, let me give those two caveats. What I've tried to do is, particularly in the how, where I've thought about, you know, the use of space, the use of the other channels, and then manipulating and multiple views and reducing, I do think of this as reasonably complete. However, if I had $100 million to bet, would I say that this is the final answer and we're all done? Well, no. I wouldn't bet $100 million on that. On the other hand, if we're talking about, you know, $20 that we're betting, and you were to say, you know, 3 years from now, could you go through pretty much every paper at Viz and end up categorizing its choices into one of these bins usefully? I'd say, yeah, I'll bet you $20 on that. Now, the place where my willingness to bet is going way further down, for example, I don't think this is complete. I think that this taxonomy of tasks is fairly high level. I think one of the really interesting parts in Viz is going to be coming up with either, hopefully not domain focused, but ideally at least like data set focused, like what are the set of tasks for networks? You know, there's been papers written by people like Bangshin on, you know, let's have a typology of network visualization tasks. There's been other work as well. So, you know, we just had a paper last year at Believe on what are the tasks for working with dimensionally reduced data, where you actually end up adding quite a bit more precision. So I think this is a start. It's a better start than I had before. And even this, for those of you who know the paper from last year on a multi-level taxonomy for tasks, notice how there's a bunch of stuff in this version in the book that wasn't in that, in part because of page lengths, but in part because we spent more time thinking. So I feel like this is very much sort of evolving. And then on the data set front, you know, I don't think this is necessarily the final answer either. In particular, I mean, I went back and forth a lot about these questions of spatial field and, you know, geometric stuff in and of itself. And notice how there's this grab bag of other stuff. This was the miscellaneous category, right? So suddenly there's all these papers on sets. You know, at InfoViz this year, there were 3 papers on sets. You know, lists, clusters. So I don't think any of these is the final answer, but I think they let us try to come up with some kind of shared vocabulary for now, and people will propose additions to the vocabulary and changes and refinements. So I don't think that necessarily these particular diagrams will be the final answer 200 years from now, but I hope they give us a place to have a discussion about the next set of building blocks and define these guidelines between them, which I think is a really interesting part.